Let's go through a few conceptual questions relating to impulse and momentum. So go ahead and read through this and determine what you think your answer is. The correct answer is A. There's a few ways to reason this through. One of them is just to think about, okay, the ball is hitting the floor. Even though the ball is coming at an angle, if we were to imagine drawing a free body diagram of the ball while it is in contact with the floor, of course we'd have the force of gravity, and the floor, because it is a surface, would push upwards. Remember, free body diagrams would not have velocities in them. And so the floor is simply pushing straight up. So impulse, we can talk about as, or at least approximate, as the average force that the floor specifically is applying to the ball while it's in contact. So that average force times that small time frame in which they're in contact, but that is also equal to the change in momentum, meaning mv final minus mv initial. Personally, I think this particular question, it's easiest to just think, well, the force is pushing up, so the impulse has to be straight up. We can, if we would like, talk about the V final minus the V initial. If you remember, in pictorially subtracting vectors, I would draw V final first, and where I ended that, I would subtract V initial, meaning it needs to point in the opposite direction. So delta V is straight up. Now momentum is not delta V, but the ball's not changing mass. So we can technically factor M out and say this momentum for the ball in this specific case is its mass times delta V, meaning the direction of the impulse has to be the same as the direction of the change in velocity. So we could reason it out that way as well. Let's look at another one. Now this one does require a calculation, but if you've never solved one of these before watching the solution, this is the one to do. Really, they are all good to do. All right, so we want to find the impulse. Initially, my ball is headed towards the wall, so V initials to the right at 20 meters per second in my picture. Finally is to the left at 12 meters per second in my picture. We don't have to have the wall drawn to the right. We could have the ball headed toward the wall to the left. Impulse, in this case, because I've been given mass and velocity, I would use the relationship that impulse is the change in momentum, meaning mv final minus mv initial. In this coordinate system, v initial is positive, v final is negative. The mass, V final, I would want negative 12 meters per second, and then I'd want to subtract my initial. So 0.2 times negative 32 is what, 6.4? I know I should be able to do basic math, but sometimes I have a hard time with it, and I use my calculator. So this impulse, now my answer technically comes out to be negative. But that's because of the way I drew my picture. If we had drawn the ball coming from the right and bouncing off, we'd get a positive. So ultimately, because the problem didn't give us a coordinate system to work with in specific directions, all we can do is give the magnitude. So 6.4 newtons times seconds, we could say it's just directed away from the wall. That's the best we could do in terms of describing direction. Vectors are back. The direction of the velocities are important when we talk about impulse and momentum. So make sure you put on the flashing lights, whatever it is that's going to help you remember to use our vector math that we learned earlier in the semester in solving these problems. Okay, I have a couple more concept questions. First one is here. What do you think the answer is? So, answer C is correct. You've seen a similar question to this before, only it asked which one experienced the larger force. If you remember, Newton's third law tells us that whatever one object does to the other, whatever force, for example, whatever force the mosquito applies to the truck, the reaction, the truck applies the same but oppositely directed force to the mosquito. So Newton's third law, they have to experience the same magnitude of force, but to relate that to change in momentum, we do that through the concept of impulse. We know impulse can be calculated as the change in momentum, but it can also be the average force times time. So the impulse that the mosquito, for example, experiences would depend on the force it feels, on average, from the truck, times the amount of time that impulsive force, just that big force in the collision, is applied. Well, similarly, the truck, the force it experiences from the mosquito is same size, same magnitude, same number of newtons, just in the opposite direction. That impulsive force exists for the same amount of time because that force is the force they're exerting on each other. If the forces are the same, then the impulse has to be the same in magnitude or size. They'll be oppositely directed. Impulse is a vector, but they will have the same size of impulse. Okay, one more concept question. Now, just side note, by large wooden bowling pin, I mean like outside of the bowling alley. If here's the door, we can walk in, here's some windows. We're talking like the big pin outside the bowling alley. That's a terrible picture. It doesn't have to be that big compared to the building, but something big as a decoration, not the actual pin that you would be hitting with the bowling ball. So, which ball is most likely to topple this bowling pin? So imagine the bowling pin is like the height of a table or the countertop or your car. We know, as far as our concepts right now, we can say the impulse on this pin would depend upon the average force the pin experiences from either ball, the ball of putty, meaning it's going to stick, or the rubber ball, like a racquetball, one that's going to bounce off. So ultimately, the one that can apply the biggest force, or for the longest amount of time, but that time, we have to be really careful with this delta t. We mean specifically just that very short time where we're considering the collision part as an impulse. So even though the putty sticks to the pin, we're not talking like that forever amount of time it stays sticking there. We mean that initial collision where the putty gets stuck, just that tiny time frame. We know that impulse can also be calculated by changing momentum, meaning final momentum, which we could write as mv final, minus the initial momentum, mv initial. In this particular case, I want to relate my force to this change in momentum. The balls themselves have the same size and mass, according to the problem, the question. So the mass of the ball is not going to matter. Ultimately, the ball that has the largest change in momentum is going to apply the biggest force. Well, the rubber one that bounces, we have a V initial towards the wall and a V final away from the wall. The one that sticks, we have a V initial towards the wall, but we have a V final of 0. If you went through that previous question, when we account for directions in the delta V, we would have to put the negative value of V final to account for it moving to the left in my picture, minus the initial value of the velocity, because we're taking delta V as a V final vector minus a V initial vector. So we have to account for the direction as we do this math. So ultimately, for something that bounces off, we get a relatively large change in velocity because of that change in direction. For something that sticks, the delta V, well, the final velocity is 0 because it's stuck to the pin, minus the V initial. So the ball that bounces off is going to have a larger change in velocity, which means a larger change in momentum. So it will apply a larger force, or it experienced a larger force from the pin, which means it applied that same larger force to the pin. So the rubber ball, the one that bounces off this wooden bowling pin, would be most likely to make it fall over. Now, either one could technically make it fall. It depends upon its mass and how large its base is. But the rubber ball would be much better at making it fall over.